ladies and gentlemen, this is going to be your note set for the front side of your notes today for equilibrium constants. So I want to start out by talking about what we've covered so far having to do with equilibrium. We've talked about that equilibrium is when a reaction can proceed in both directions. We can get the forward reaction and the reverse reaction happening simultaneously. We've also covered Le Chatelier's principle, which is basically how stresses are going to affect a reaction that's in equilibrium, how they're going to shift forwards or backwards, etc. And we've also talked about how that forward and backward shift can affect the concentrations of products and the concentrations of reactants, respectively. You did a worksheet or should have done a worksheet about this already. So to move on, equilibrium constants are a value that is abbreviated K sub EQ. So we are actually seeing that value pop up right here. And that KEQ is a value that is calculated by effectively dividing your concentrations of products by your concentrations of reactant. And in that calculation, each concentration is going to be raised to the power of its coefficient in a balanced chemical equation. So we've been working with balanced chemical equations all over the place. You should have those pretty much down by this point. So what that equilibrium constant is able to tell us is which side of that reaction is favored at equilibrium. Are products favored at equilibrium or are reactants favored at equilibrium? Because we've talked about the fact that at equilibrium, our concentrations of reactants and products are often not the same. And you saw that during our snowball fight as well. Sometimes there were way more of those little snowballs on the product side. Sometimes there were way more of those little snowballs on the reactant side. It kind of depended on reactant conditions. So, to give you an idea of what an equilibrium constant expression would look like, we have this sample reaction here, which obviously is not a proper chemical reaction, but it is just a little bit of a baseline so you can get the idea of what that expression is going to look like. So we know already, because I told you, that equilibrium constants are products divided by reactants. So I'm going to use blue to represent my product numbers, and I'm going to use red to represent my reactant numbers, and I'm going to try to carry that through the rest of this note set. So if I were to write the equilibrium expression for this reaction, I would put my products on top, and my products are C and D. So products are, again, any chemical. It could be water, it could be sodium chloride, it could be whatever. But we are going to express those product concentrations in brackets. And that's a bracket if you weren't sure what that is. So my product, that capital C, is going to be raised to the little c, which is its coefficient. And then that is going to be multiplied by the concentration of reactant D, which is raised to its coefficient. All right? And so we're going to take that and we're going to divide it by the concentration of reactant A raised to its coefficient times reactant B times it to raise to the power of its coefficient. And that is a general equilibrium expression. So a couple of things to note about equilibrium expressions. So I'm just going to zoom in and move a little bit so you can see it a little bit better. What can KEQ tell you? Well, we talked about that a little bit already. It indicates whether or not the products or reactants are favored in an equilibrium system. So if you have a KEQ that is greater than 1, that means that our reaction is going to generally move forward. It's a forward favored reaction, which means that at equilibrium there are more products than there are reactants. If I have a KEQ that is less than 1, that means that overall the reactants are favored at equilibrium. Overall, that back reaction is going to be favored, that reverse reaction, and there are going to be more reactants than products at equilibrium. And if we look at the general KEQ expression up here, that kind of makes sense, because if I have a ton of products on the top, but not a lot of reactants on the bottom, that means that my number, when I divide all this out, is going to be pretty big, and so therefore it's going to be greater than 1. But if the opposite was true, and I had a really big number on the bottom in that red zone, and a really small number on the top, then I would end up with a KEQ value of less than 1. So that kind of should make a little bit of sense to you. There are a couple of things that you're going to leave out of any equilibrium constant expression. Anything that is in solid state or in liquid state should not be included in an equilibrium constant expression. You are only going to include gas phase and aqueous phase. And the reason that we leave out solids and liquids is because they are said to have an essentially constant concentration. So if that's not changing overall in the course of the reaction, it's okay mathematically to just go ahead and leave it out. So let me zoom back out, and we're going to go do a couple of practice problems together. We have practice problem number 1 at the top here, and it says a liter of a gas mixture at equilibrium at 10 degrees Celsius contains 0.0045 moles of dinitrogen tetroxide and 0.030 moles of nitrogen dioxide. And it wants us to write out the equilibrium constant expression and calculate the KEQ for that reaction. So, keeping in mind over here that we know how to write a KEQ equilibrium constant expression already, that's products divided by reactants, we're going to identify those things. We know that anything on the right-hand side is considered a product. We know that anything on the left-hand side is considered a reactant. And so in our equilibrium constant expression, I can write that out real quick. We have KEQ is equal to our product divided by our reactant. Whoops, wrong color. And so in our equation that we're seeing over here, our products, we only have one of them in this case. We have NO2, nitrogen dioxide. So in my constant expression, I should have nitrogen dioxide over here. And since we see that there is a coefficient of 2 in front of it, I'm going to raise it to the power of 2. Just like over here in my original generic one, all of those reactant and product molecules were raised to the power of their coefficient. Now, my reactant molecule, again, I only have one of them, is N2O4 dinitrogen tetroxide, and we see that there is, in fact, no coefficient in front of it, which means, as we know, that that is a nice implied 1. So I don't have to raise my concentration of dinitrogen tetroxide to any coefficient whatsoever. I'm raising it to the coefficient of 1, which doesn't do anything mathematically. So I'm going to plug in N2O4, and you can put 1 in as your power, or you can leave it blank. Either way is fine with me. Now, we've written out our generic equilibrium expression. Now we have to start filling in numbers, so we got to do a little bit of interpretation in the problem. We know that the product is nitrogen dioxide. So I'm going to go ahead and underline the moles of nitrogen dioxide in my blue product color. And I'm going to go ahead and underline my moles of dinitrogen tetroxide, my reactant, in my reactant color, because those are the numbers that we are going to plug in. But before we plug in those numbers, I want to point out that it says a liter of gas, and it gives us the amount of moles. So if we remember from our solutions set of notes, molarity, which is a concentration, is equal to moles divided by liters. So if I have 0.0045 moles in a liter, that is going to be equal, for my red reactant, it's going to be equal to 0.0045 divided by my singular liter. So that 0.0045 is my concentration. And the same could be said for my 0.030, because I have that many moles in 1 liter. So I can do 0.030 divided by my 1 liter and get 0.030 molarity, which is, again, my 2 concentrations that I'm going to plug in to my constant expression over here. So let's go ahead and do that. My product concentration is my 0.030, so I'm going to go ahead and bring that down. And I'm going to raise it to the power of 2 because that's what it says to do in the equilibrium constant expression that I just wrote over here. Now on the bottom, I have my other concentration, my 0.0045. And that one was not raised to any specific power other than 1, so I can just go ahead and go 0.0045. And again, that is all equal to my KEQ value, which is what the problem wanted me to figure out in the first place. So if I plug all of that into a calculator, if I do 0.030 squared and then divide that by 0.0045, you should get that your equilibrium constant is 0.20, and that is going to be your answer for this problem. Now I want to talk about units really quickly. There is no unit for KEQ, and the reason for that is because your units on top and bottom are both molarity. They're both concentration, so they end up actually canceling each other out mathematically when we do this. So this is our answer. And if we wanted to do a little bit of analysis, we see that that 0.20 is less than 1. So if I were to ask, you could say that the reactants are favored at equilibrium and not the products. So what you should do at this point is you are going to want to pause the video and I want you to try number 2 on your own. Obviously, I don't have control over whether or not you actually do that, but it would be a very good idea for you to take this opportunity and do a practice problem yourself. So I'm going to pause for a couple of seconds, take this opportunity to pause, try the problem yourself, and then you can see how I work it out. All right, so whether or not you took my advice, here is the actual solution here. This problem starts with a sentence saying bromine monochloride decomposes to form bromine gas and chlorine gas. Write and balance the equation for this reaction in the space below. So here's a little bit of older skills that we're seeing. You haven't written and balanced a reaction in a little bit, but let's take a second to practice it. Bromine monochloride would be BrCl. That's a covalent molecule. And I will tell you, because this problem doesn't tell you, but I will tell you that that is going to be a gas molecule. So we're going to assign it the gaseous phase. Now we are told that that decomposes, which means it's the only reactant here. So I'm going to put that equilibrium arrow since we're talking about equilibrium. And then my 2 products are going to be bromine gas and chlorine gas. And so I'm going to assign that gas phase for both of them. I also put a subscript of 2 for both of those gases because both bromine and chlorine are diatomic elements, and as such, they get that little subscript of 2. The next thing we have to do is balance our equation. We have on the left 1 bromine and 1 chlorine, but on the right we have 2 of each, so that's easily done by just putting a little 2 right out in front of bromine monochloride. So now we have our balanced equation. So it's time to identify what we're looking at. I'm going to again circle my products with my product color. I'm going to circle my reactant with my reactant color just so it's easy going forward through the problem. And over here on the side, I'm going to write out my equilibrium constant expression because this is an equilibrium constant problem, and so I'm going to need it. I know that my KEQ is going to be equal to my product concentrations, which is my bromine times my chlorine. Neither of those have coefficients in front of them, so I don't need to raise them to any power. And we're going to divide by my concentration of BrCl, but that does have a coefficient of 2, so I'm going to square it. Okay. Now let's move on. Let's look at what the rest of the problem wants this to do. It says, using the reaction that you wrote above, calculate the concentration of bromine monochloride at equilibrium if the KEQ for the reaction is 11.1, and the equilibrium concentrations of chlorine and bromine are both 4.00 moles per liter. Assume the reaction takes place in a 1 liter container. Okay, so we're given a lot of information. So the first thing we want to do is figure out what we are being asked to do, and that tells you in the first sentence. It says, using the reaction that you wrote down, calculate the concentration of bromine monochloride. So we do not know our concentration of our reactant. So I'm going to put a little question mark next to it. We are, however, told that the KEQ value is 11.1. Right? So we're told that bit of information. And we are told the concentrations of both products. So chlorine and bromine gas have this concentration, and it is expressed as a concentration in moles per liter. So I have all the pieces and parts. I need to solve this problem. I know that my KEQ from my equilibrium expression is going to be 11.1 because I'm told that in the problem. So 11.1 is equal to my products divided by my reactants. So my two products are both at the concentration 4.00 moles per liter. And I again know that because I am told it. So in my numerator, I'm going to have 4.00 twice. Then down below, I have the thing that I don't know. I have my bromine monochloride, which I am going to express as X because I do not know what it is and I'm going to solve for it. And that X is squared because, again, in my little constant expression up here, I knew that it was squared before. So mathematically, now I have to rearrange this whole thing to solve for X. So the first thing I'm going to do is I'm going to multiply both sides of this equation by X squared to get it out of the denominator, and I end up with 11.1 X squared over here, and that is equal to 4 times 4. So I'm just going to simplify that and write 16. Then I am going to continue to solve for X. I'm going to divide both sides by 11.1. Divide that side by 11.1, and then I am going to get, over here I'm going to start writing that X squared is equal to, again, 16 divided by 11.1 is going to give me 1.44. But I'm not done yet. I have to square root that because I have to get X, not X squared. So I'm going to square root both sides, and then I get that X is equal to 1.20. Yes, your calculator number will be a little bit different, but again, I'm rounding for sig figs, and I notice that every single number in my problem has 3 sig figs, so I am rounding this answer to 3 sig figs. Now, in terms of units, we have to talk about. The thing I was solving for was bromine monochloride. That's what this is, and since I'm solving for a concentration, my unit is going to be moles per liter. You could also have said capital M for molarity. That's also fine. You can use either one. It does not matter to me which one. But that is how to write equilibrium constant expressions. I hope that that was helpful for you. If you have questions, please come talk to me.